Hello and welcome. In this video, we will look at high availability, fault tolerance, and see how critical systems are able to achieve 5 nines, or in other words, systems are able to remain up 99.999% of the time. We will also look at how systems upgrade or downgrade their software while still remaining up and running. This video is divided into 3 sections. The first part talks about fundamentals of redundancy and high availability and its architecture. The second part talks about how software upgrades and downgrades can be done without any downtime. And the third section talks about some of the ways in which high availability typically can be implemented. So let's get started. A typical client-server architecture contains a server with an interface visible to an external world, which is then connected to many clients or external interfaces. The server provides services which are consumed by the clients, and the server is expected to be up 99.999% of the time. To achieve this high availability, the server system contains an active server and a standby server. The active server does all the server functionality and processing, while the standby server or the standby system does some backup activities. Now, what are those backup activities the standby system does? It does two primary activities. The first thing it does is take regular sync from active system. This sync is a sync of the state of what the active is doing. So, if the active process is doing certain functionality, it also informs the standby system that I am doing so and so task, and this is what I have done and this is what is pending. For example, if there are, let's say, 10 clients connected to the server, and let's say the server has processed certain percentage of tasks for all the 10 clients, all these details of the 10 clients will be synced from the active to standby, and the standby will know all details of the clients and how much work has been completed for all those clients. Typically, the standby system will know the complete details of what the active system has been doing till now. Apart from this, the standby system will keep sending regular heartbeat pulses to active, to which the active system will need to reply. This heartbeat is necessary to make sure that the standby knows that the active is up and running and functioning as expected. Heartbeat pulses are exchanged every few milliseconds, so that if active goes down, the failure is detected as soon as possible. Now, all the client services are processed by the active system. No matter how good a software or hardware is, one cannot rule out bugs, errors, and unexpected circumstances. So one cannot rule out a failure. If the active system fails for whatever reason, there could be a software bug, a process crash, a hardware failure, a power failure, or whatever could be a reason. The heartbeat failure from the active is detected by the standby system. Once a heartbeat failure is detected by standby, it immediately triggers a switchover to become active. The standby system already knows what the now defunct active system was doing at that time and takes over all the tasks. Whatever connections which were established with the previous active are now continued with the new active. Note that all this happens in a few milliseconds, so the clients don't even realize that there was a failure on the other side. The old active, which had crashed, now reboots and comes up as a new standby. It then starts receiving sync information from the new active, as well as starts exchanging heartbeats from the new active. This is how high availability is achieved in many of the solutions which are present in today's world. From the external world point of view, the server system still appears up, while internally on the server side there was a crash or a reboot and systems might have restarted. Similar setup is also used for software upgrades and downgrades. Now let us see how a HA setup is used for achieving a software upgrade or a downgrade. Note that this kind of approach is typically used in many of the systems to upgrade the software with minimal downtime. In an in-service software upgrade, the primary requirement is to have the system available for clients throughout the software upgrade process with no downtime from client's perspective or client's point of view. Before software upgrade is started, both the active system and the standby system are running the old version of software. As a first step, the standby node is loaded with a new version of software. Once the standby is up with new version of software and it has established heartbeat with active and received all the state information from active, a switchover is triggered in step 2. In step 2, the new version of software becomes active while still retaining all the existing client sessions. There is no impact to any of the clients. At this point of time, the old version of software could still be running on the standby. In step 3, the old standby is rebooted and it comes up with new version of software. And then it establishes heartbeat and syncing mechanism with the new active. So with this, we successfully transition from an old version of software to new version of software without having any downtime from the client's perspective. Now let's see some typical redundancy implementations in systems. The simplest form of redundancy implementation is having an active process and a standby process running in the same system. Both these processes will be running in the same operating system, and while the active process will do all the tasks, the standby process will just keep maintaining the state of the active process and be ready to take over if active process crashes. The advantage here is there is no redundant hardware, or rather, one does not have to invest on additional hardware. But the disadvantage is if there is any hardware failure, the whole system goes down. So one can protect the system from software failures, but one cannot protect the system from hardware failures in this case. A similar approach is done in the virtual machines domain. The only difference here is instead of spawning processes, you spawn virtual machines. We have an active virtual machine and the standby virtual machine. Again, this provides software redundancy, but if there are hardware failures, then those are not protected. To protect from hardware and software failures as well, one needs to have a redundant hardware and redundant software. Hardware redundancy typically has two identical devices, one of them running as active device and another running as a standby device. One can have redundant power supplies or redundant databases or redundant routers, etc. Another form of redundancy is to handle natural or man-made calamities like storms, earthquakes, war, cyber attacks, etc. One can have an active data center in one geography and a standby data center in another geography. This is called geo-redundancy. Typically here, redundant devices are separated across geographies so that at least one of those devices is available at any given point of time, even in case of natural or man-made calamities or disasters. So that gives a brief on redundancy architecture, how it is achieved, and what are the typical ways in which it is implemented. I hope you find this video useful. So until next time, see you. Goodbye.